We're asked to use the trapezoidal rule to approximate this integral. So remember what we do with integrals. Integrals, this is from 0 to 2 on the x-axis, they tell us the area under the curve between two endpoints. So between x equals 0 and x equals 2, what is the two-dimensional space right here? Because I graphed x squared. We all know what that graph looks like, right? So it's a curvy piece, so we can't use like a triangle. The triangle would approximate the area, but it wouldn't get it right. We have to use calculus to get the exact area. And so you might know, like, hey, I know I can use the power rule in reverse. This is going to be 1/3 x to the third for an antiderivative, and I just plug in my limits of integration. That's what you do with the second part of these instructions. The first part asks us to approximate this area using something called the trapezoidal rule. Okay, and the trapezoidal rule is pretty straightforward. All it's asking you to do is to break this into 4 chunks. So since we're going from 0 to 2, that means 0 to 0.5 is a chunk, 0.5 to 1 is a chunk, 1 to 1.5 is a chunk, and then the fourth chunk is between these two. So 4 chunks, and then draw trapezoids to approximate the area. So remember, a trapezoid has 2 parallel lines. That's a trapezoid. So we can do that here by using the left and the right endpoints. So it'll actually be probably easier to see with this one over here. I can draw a trapezoid going from here for one endpoint, and then this is the other y coordinate I have up here. From 0.5, this is where we are on the graph. To 1, this is where we are on the graph. And if I draw a vertical line down, I've created a red trapezoid here, right? To find the area of a trapezoid, it's the average of the bases times the height. So for this red trapezoid I just drew, this base, I need to know where we are on the y-axis to know how high up we've reached. And to figure that out, this is the curve. All we have to do is plug in 0.5 in for x to find out the corresponding y value. So if I plug in 0.5 in for x, that means I just have to square it. So 0.25 is the corresponding y value here. This is y equals 0.25. And then the same thing over here. If you plug in 1 into your function, the y value you get out, 1 squared is 1, right? And so the area of this trapezoid is the average of the bases. So this one is 0.25 in length, and this one is 1 in length. So we divide that by 2. And then you multiply it by the height of the trapezoid. So the height of this trapezoid is 0.5. Right? From 0.5 to 1, you've got 0.5 in distance. And so that's our first area. Okay. Again, this trapezoid, if I was to draw it off to the side, it looks something like this. We found out that this side was 0.25 in length. This other base over here was 1 in length. And then this part across is 0.5 because we have 4 subintervals, we call them. So the area of that trapezoid is right here. So you just got to do that 4 times, once for each region. So over here, this trapezoid starts here, ends 1.5 on the x-axis. So we got to figure out what the y value of this is. So we just got to plug in 1.5 back in for x. So this is going to be a y value of 2.25. So this new trapezoid, if I draw it off to the side, it's 1 for one of the bases, it's 2.25 for the other base, and then on the x-axis it's still a height of 0.5. So the area of our next trapezoid is the average of the bases times the height. So we've got 2 down. Took care of this one. We'll keep going because the last one looks a little weird. This next one is 1.5 to 2 on the x-axis, so we have this base. We need to know what this base is. So if you plug 2 in there, you get out 4. So this is going to be plus the average of the bases, 2.25 plus 4, and then we divide it by 2. Then we multiply it by 0.5. And then the last one is going to actually be a triangle, right? Because this has a height of 0 first for the left endpoint. And the right endpoint has a height of 2.5. So 0, you could use the trapezoidal rule, or you could just say, hey, it's a triangle, and it's 1/2 times base times height. But I got 0 plus 0.25 divided by 2 times 0.5. And then once you compute all these, you'll have your approximation using the trapezoidal rule. So 1.25 divided by 2 times 0.5. So here's my first trapezoid that I wrote down. The second one is 3.25 divided by 2 times 0.5. This is the second trapezoid. So that's 6.25 divided by 2 for the biggest one. There's our third trapezoid, and then we went back to the beginning because it didn't really make a trapezoid. It made a rectangle. Sorry, it made a triangle. I gotta relearn my shapes. Huh? Okay, then if we add these all up, .75. That's our approximation for the area under the curve. And you might be thinking, why do we even do this in the first place if we know the exact methods? It's because there's plenty of functions where finding the integral is prohibitively difficult. It would take too long to try to think of some crazy math rule to actually evaluate the exact integral. And since we have computers, we can approximate the area very well by taking not 4 subintervals here, but if we took like 1,000 subintervals, we get really, really close. So close that now it doesn't really matter about finding the exact interval. Okay. And the trapezoidal rule, the whole reason we're learning that after learning all those left rectangular approximation methods and right rectangular, the trapezoid is a better approximation for the area under the curve. So we said it's approximately equal to 2.75. That's the first part. That's the trapezoidal rule. To find the exact value, this one we can find exactly. If this is a real world problem, we wouldn't need the trapezoidal rule because the function's simple. It's just x squared. So the antiderivative is x to the third over 3, because if I was to take the derivative of this, the 3 would come down, multiply, and then get reduced by 1. And it would turn back into x squared like we wanted. So we just got to plug in the limits of integration. So 2 to the third is 8 thirds. 2 to the third over 3 is 8 thirds. So that's the exact area under the curve. So that shows you that we overestimated using the trapezoidal rule. Should be 2.6 repeating. We got 2.75 using the trapezoidal rule. But that's okay. We know it's an approximation method.